Welcome to a lesson with Dr. Powell. Let's look at another related rates problem. Suppose, for instance, we have a cone, and maybe it's a tank of water, and perhaps it's leaking. So out the bottom, we know it's leaking some water, and maybe perhaps at the rate of let's do maybe 0.2 cubic feet per second. All right, and let's suppose that the height of this guy is okay, so let's suppose that the initial, okay, so let's suppose the height of this is 4, and let's suppose that across this way we have 2. Okay, so then the question is, right at a particular instant when the height actually is 3, so it begins at 4, but right here at this instance at 3, I want to know what, and suppose this is the height of the water. I'm interested to know what dH/dt is right then. What is it equal to? Okay, well, let's get started and find out what it is. All right, so we know how fast the volume is being depleted, but how fast is H going downward? Okay, well, we can use the idea of the equation of a cone to kind of get this working right. We need to be able to know how much volume we have at a particular point in time. We're going to let H stay variable right now. We'll plug in 3 in a minute, but we need to keep it variable so we can find relationships between rates. Okay, so we need to be able to kind of have a relationship between V, well, what? We know this, what does that mean? That means something to do with volume. So I'll say dV dt is equal to negative 0.2. So because it's going down. So dV dt is equal to negative 0.2. So that means we need to have a relationship, first of all, between V and H before we can have a relationship between dH dt and dV dt. So V is like this volume in here of the water. So we need to have an equation that relates V and H. Well, if we think about a cone, it follows the 3-dimensional version of a triangle equation. Instead of doing 1/2 base times height in 3 dimensions, we do 1/3 base times height for such a triangle. The base right here is just the area of a circle. So pi times a radius squared, and then you multiply by H. Okay, so this radius, though, really is dependent upon how high we are. We could think about ratios of similar triangles. Think of this as a 1. Go down here and think of, we have the ratio from radius to height is 1 to 4. So to know what the radius is, it's going to be 1/4 of whatever the height is. Well, if the height is H, remember, don't use 3 because we need to keep things variable. So the radius is going to be 1/4 of H. So we can use that right here. Let's write down 1/4 of H, but then we have to square it because that's R squared pi. So really we have a relationship between V and H. We have an equation relating V and H. All right. So from that, let's figure out what we can do. Now, since we have an equation relating V and H, the next step is to find to take derivatives to find a relationship between dV dt and dH dt, everything with respect to t. So I'm going to rewrite this as V is equal to pi over 16 times H cubed. I just kind of worked that H squared and H cubed and then 1 over 16. Okay, so something like that. So dV dt is going to be equal to pi 16. Take the derivative with respect to t, so H is a chunk, so there's a composition involved. So you have to have a multiplication, dH dt, and that was important so that we could get the dH dt out. So now, to find dH dt, we can simply think, okay, at this particular instant in time, H is 3. So since h is 3, you can plug that in, and you get 9 times 3, so 27. So 27 pi over 16 is equal times dh dt is equal to dv dt, which is negative 0.2. So that means that dh dt will be equal to, let's see, negative 0.2 multiplied by 16 over 27 pi. And if this is feet, okay, feet per second. So that's how fast it's going downward here. Can be figured out by simplifying or working that out right there. Thanks for watching.